So we've seen some of the applications of the gradient. Another very useful application of the gradient is its ability to relate a scalar field to the vector field. And what we'll consider here is called a potential. One of the examples is the electric potential. That is, a scalar field which is related to the vector field, and both are describing the electric phenomenon. So you see the definition that this electric potential is the scalar field which is converted to the electric field, which is vector field, if you take a gradient of that potential and put in front the minus sign. So that's the definition. So it's a minus gradient of the electric potential is the electric field. Let's look at the example. Let's take an electric potential at the origin for a point charge. Point charge means that you have really small size of your charge relative to the size of your area of where you conduct your experiment. And here the Q is the value of this charge, and the epsilon naught is some electric constant, and R is the distance from the origin, which is defined as what's called Euclidean distance. So it grows as you move forward. And what we want to know is we want to know the electric field corresponding to this charge if we know its potential. So its potential drops as we go away from the charge, and we want to know how the electric field looks like. Let's use the definition. So by definition, the gradient of any scalar field included in the potential is just a set of its partial derivatives multiplied by the unit directions. And we can ignore all these constants for time being and just compute a partial derivative of that function 1 over r, which depends on x, y, and z. It's not straightforward because it's quite a complex function. Let's start with the x. Let's compute the derivative of that function with respect to x. First, we'll know that you can write it slightly different way using the negative power. And then let's just see what we get. Well, first we will just again remind ourselves that we have a function in effect of 3 dimensions, x, y, z, which is x squared plus y squared plus z squared to the power of minus 1/2. So let's take a partial derivative of that function using the chain rule. So that's what will help us here. So we take that expression inside and differentiate it with respect to x. Minus 1/2. So first we'll get minus 1/2 times that expression, and then we get the 2x from the inner part. And if we simplify it, we write minus 1/2 2x over x squared plus y squared plus z squared, and this is to the power of 3 over half, or we can simplify it further and write it as minus x over square root of x squared plus y squared plus z squared, everything to the power of 3, and else we can say that it's x over r, where the user definition of r. So that's what we found, and very much in the same spirit we'll find that if we differentiate with respect to y, we will get minus y over r cubed. Sorry, here is r cubed, right? Because we take this bracket. And likewise, we see that if we take with respect to z, we'll get minus z with respect to r cubed. So if we put these things together, we'll see that we have minus x over r cubed, minus y over r cubed, and z over r cubed. And if we simplify it a bit further, we see that it's in effect just the components of this vector r, which points away from the charge. So that is actually what the electric field looks like. It's a vector, not scalar field. And if we use this notation that r, which is now note here, it's the vector r, which has a direction, then we can write it this way, much more compact form. So it's a charge over the electric constant, inverse square of the distance, and then r over r. This vector r over its magnitude. And if you take the minus sign, we'll get the electric field. So, as I said, the r over r is a vector which actually has a magnitude of 1. Right? Why does it have magnitude of 1? Because if you take magnitude of r over r, you can take away r, and you will be left with this, and this will be just r over r, which is 1. Right? So its magnitude of this vector is 1. And so what it actually tells you, that formula, it tells you that if the charge is positive, then the electric field points in the same direction as the moving away from the origin, and it has this magnitude, so it falls inversely proportional to the square of the distance, similar like gravity. And if charge is negative, then everything is the same magnitude, but it points to the opposite direction. So what you actually can see here is, if you again try to visualize what actually is happening, you can plot a case 1 where you have your charge in the middle, positive charge, and then you have a set of lines of constant potential around that charge, and the direction r is the direction of your field. So if you plot the lines corresponding to the lines of electric field, they will follow just different directions. So this actually can be also called the direction of the electric field. So it will have a series of lines radiating from the center. So this is what is the picture for the positive charge. And for the negative charge, the story is almost identical, but instead you will have lines pointing to the opposite direction. So instead of having that, you will have everything converging to the charge. And the charge itself is negative here. But you wouldn't be able to tell it from just looking at the lines. So that line corresponds to a constant potential. And the gradients of that potential will be the electric field, the minus gradient. So that's all we want to know about electric potential for now.